Well, you are already acquired knowledge really to suppress intuition and logically make conclusions about things. And I want actually to test it. I'll have a puzzle with the yo-yo, and I want you to figure out what is, analyze and predict the future. So I want you to figure out what will happen with the yo-yo when I pull the string. You may have a brief conversation for a moment. And I'm not interested really what will happen. I'm interested more in your justification of your prediction. And we will actually see the justification on the whiteboard. So consult with each other. Yeah, because I bet that everybody thinks that it will go that way, right? Why? Can you give a good justification that it is going to roll to your right? Well, let's take a look at the interactions. Yeah, so here is that yo-yo, and the string is one over there, and I'm going to pull it here. So let's figure out what are the other interactions and figure out why is it going to roll, where it is going to, when it is going to roll. So can you find other forces? There is a normal force, right? And normal force is exerted by the table, so it is at this point, right? And it touches practically with one point, so there is one particle on which that normal force is exerted. Oops. Okay, what else? Weight. Okay, where should I mark weight? Not center of mass. Which center? Center of gravity. They overlap, but I want you to recognize the difference at the center of gravity. Correct. And it happens indeed that center of gravity is at the geometrical center of yo-yo, so it will be from here. What else? There is a frictional force exerted by the table on yo-yo. Which way? To the left. And it's also, contact is over here, so it will be to the left. Static or kinetic? Static. Well, tension is the same really as this one. So in principle, yes, it's the same force. What else? That's it. Correct, that's it. All right. Now figure out, so bring up appropriate law which says how it is going to move. And you can bring several of them. Pick the one which is most convincing. Probably the first thing which comes to your mind is Newton's second law, right? Which version? Which one? Oh, a lot. You have the suggestion of the first one finds a strong opposition. Why? Because it doesn't look like a particle. It has a lot of particles, so there is a problem with that. Well, but however, when we were talking about approximating objects by particles, really we were using a different version of Newton's second law, right? Which one? I mean, I'm not interested in the number, but tell me what was related to what. Yes, so the net force exerted on the object was equal to product of mass of the object multiplied by what acceleration? We are talking about the object. Which one? Oh, there is total acceleration. There is no such acceleration as total acceleration. Acceleration of the center of mass, correct. Let's try to use that. Yes, so we have one force up, one force down, one to the right, one to the left. Which way is the net force? I mean, it's easy to figure out, well, that these two balance each other out, right? So these two add up to 0. Normal force and weight add up to 0. But how about friction and the tension force? Well, but our problem is, well, the tension, I determine the tension. Depending on this, how strong I pull, I determine the tension. Frictional force adjusts itself. How do I know that it will not adjust itself to be always stronger? Well, the only reason that it is not stronger is if the yo-yo indeed rolls to the right. If it rolls to the right, I will recognize that acceleration is to the right, and therefore this force has to be greater than that one. But can I find another argument to show that definitely it is going to roll to the right? Yes, let's take a look at the torque. All right, now we can use torque about any point we want. So choose a convenient point so that definitely you will see that the torque is in such a direction that it will start rolling to the right. Yeah, let's now, so which point would you like to try? This one? This one? Let's use center of mass, correct. So if we use center of mass, what is gravitational torque? 0. Normal torque? 0. Correct. Torque, this torque. Which way? In, right? Right hand, Andrew, right? Right hand. Frictional torque, also in this direction, right? So we see that the torque will make the net torque is going to make the object to spin this way, right? Which means that it is going to roll to the right. This was, however, this was not the best choice of the reference point. When you solve problems, and particularly in statics, then choose a point so that you can make as many torques to be 0 as possible. So try another point. Point at the bottom, right. Yeah, so if you take point at the bottom, think about torque about this point. So what will be gravitational torque? Normal, frictional, and tensile? Not, it will be in, right? So acceleration is going to be, angular acceleration is going to be in. It is start to spinning this way. Well, if it starts to spinning this way, it means that it is going to roll to the right. It does. Well, I think that it was. I mean, you thought that it was so obvious, right? Your intuition already told you that it is going to roll this way. How about if I flip it? And now I pull it. Consult with each other now. Okay, so let's vote now. Who believes that it is going to roll this way? Who believes that it is going to roll that way? Majority thinks that it is going to roll that way. Okay, let's have, well, why don't you analyze that? Do the same type of analysis as a moment ago. Yeah, so let's, which, would you like to let's remember which version of Newton's second law would you like to use? For the motion of center of mass, we are stuck again because one force is to the right, one force is to the left, one up, one down, so it's hard to figure out which way the center of mass is going to accelerate using the relationship between force and acceleration of center of mass. Why don't we still consider torque? Torque about which point would you like to use? Let's try with the center of mass. So if we consider about the center of mass, gravitational torque and normal torque are 0, right? Now tensile torque here will be toward us. Frictional torque is going to be away from us, hard to say. How about if we use bottom? If we use bottom, then the frictional torque is 0, and the tensile torque is in. It's out? Yeah, from the bottom. It's in, right? Which means that that yo-yo will start spinning this way, right? Somehow it's inconsistent with your prediction that it's going to roll that way. Huh? What's wrong with the analysis? What say? I don't know. Maybe friction is in the wrong direction. What will happen if we flip friction? Nothing, because frictional, no matter which way is friction, in this analysis we really didn't care, because frictional torque was 0 if we picked that point. What axis? I mean, and we can choose that point A wherever we want. We can put axis wherever we want. Christina, why don't you pull that yo-yo? But in such a way that the students can see it. Yeah, pull to. See that? Thank you. Yeah, don't trust your intuition. Trust your logic. When we performed the analysis of the situation, it was inconsistent with your intuition. Yeah, because most of you really thought that it is going to roll the other way. Actually, how about if I put one more thing? What will happen if I pull it this way, so that the extension of the string goes through this point? Consult with each other for a moment. Actually, I heard JD's comment and I like it. What did you say? You were talking about the torque, right?
Yeah, I was saying that the force is in that direction to the axis, and there's zero torque in that force, so the only force is after.
What was the torque of resulting from static friction?
Zero as well.
Zero as well. Normal
Zero.
and gravitational
Zero.
net.
Zero.
What does it mean? What does it mean? Well, no, torque doesn't say that it won't move. Remember that actually motion of an object is determined by two things. Net force and net torque. I'm not sure if net force is going to be zero as well. Yeah, JD figured out that the net torque is going to be zero, so from that we can conclude that it is not going to spin. Right. I'll show you this. Yeah, this is the situation. I can pull it and it only slides. It never wants to spin. All right. So now I want you to learn a very important and useful theorem for mechanics, particularly if objects move and roll. If you know moment of inertia of an object about a center of mass, then you can easily find moment of inertia about a parallel axis. I mean, let's say if you know moment of inertia about an axis passing through the center of mass, then you can quickly find out moment of inertia about any other parallel axis. Well, the derivation for it is, so let's say that I have another axis. I know what is moment of inertia about axis C, and I want to find out moment of inertia about axis A. So from definition, moment of inertia about axis A, well, requires that I take product of, if I divide objects into differential pieces, I have to, for each piece I have to multiply mass of the piece by square of the distance from the axis. Well, I can recognize that this vector, I can mark it as a vector which points from one axis to the other axis, and then the distance from, use this vector here. So vector r is equal to the sum of vector d and vector r. I mean, hold on, which r prime. R prime is distance from the axis passing through the center of mass. So I wrote it that way, right? So square root of the distance is equal to the scalar product of that vector. And that this vector is equal to the sum of vectors d and r. Well, I just multiply it now. I mean, I perform operation, square it. How do I square it? What product? Not vector product, scalar product. It's a vector times vector, and the result is a number. All right, so this is what I'm going to get. The square of the first vector, square of the second vector, times plus 2 times scalar product of those two vectors. All right, now over here I can take this d in front. Yeah, d is a vector which indicates how one axis is shifted with respect to the other axis. So if I take out this d, I will get integral of all of masses of all differential pieces. So this will give me the mass of the object. Here I recognize that this expression is really the expression for the moment of inertia of the object about axis C. So I have subscript C. And now if I pull out this d, I will have integral of r prime dm. What's that? If I divided r prime dm divided by total mass of the object, what am I going to get? It's going to be position of the center of mass. Well, x and y component of position of center of mass. Do you see that? Well, now if the axis is passing through the center of mass, then it means that it's a zero vector. The position of center of mass with respect to center of mass is a zero vector. So here I have the zero, this is where I got that zero vector. Well, and we get a relationship between moment of inertia about axis A and about axis C. Now let's take a look at the at an example. Do we recall what was moment of inertia of a rod about the center, axis passing through the center of mass? No, it wasn't 1/3. It was 1/12. So moment of inertia about the center of mass of a rod was 1/12 mass of this rod multiplied by square of the length, right? If I use parallel axis theorem, what will be the moment of inertia about the end now? So moment of inertia about the end will be moment of inertia about the axis passing through the center of mass plus what? Distance between the masses square, between the axes square, right? Multiplied by mass of the rod. So I have to multiply it by mass of the rod times square of the distance between the axes. What's the distance between the axes? L divided by 2. And I have to square it. All right, so everywhere I have ml square. From this one I have 1/12. And from this one I have 1/4. 1/12 plus 1/4 is how much? I mean, so this is 3/4, right? Sorry, this is 3/12, right? Plus 1/12, so this is 4/12. And 4/12 is 1/3 ml square, which should make us happy, right? Because this is what we found directly from the definition yesterday. Now, when you apply parallel axis theorem, just make sure that you really recognize what is what of what, because a typical pitfall is that well, how about if I calculate it now? I know moment of inertia about the end. Moment of inertia about the end is 1/3. So I will use the parallel axis theorem to find out moment of inertia about the other end. So let's call it A, B. Sorry. I'm calculating moment of inertia about the other end. So it's moment of inertia about the first end plus mass of the rod multiplied by the distance between square of the distance between the axes. So it is 4/3 ml square. Are we happy? No. Yeah, because it should give us 1/3 again. It should be the same. What did I do wrong? Yeah, I did not use the axis passing through the center of mass, right? So this is wrong. Parallel axis theorem requires that you relate moment of inertia about an axis with the moment of inertia about an axis passing through the center of mass. Make sure to describe that quantity. All right. Now I would like actually to relate motion of a rigid body with interaction through the work energy theorem. We have already related it through Newton's second law, but work energy theorem is as good as Newton's second law. So I want now to make sure that we can relate interaction with motion that way as well. Actually, there will be nothing new. In principle, you know all the information. I'm just making sure that you realize that. So first of all, well, except for this one, by the rotational kinetic energy of a system, we understand total kinetic energy of the system about that point of reference. And you can choose what point of reference whichever you want. So rotational kinetic energy is not uniquely assigned. If I look at this rod over here and let it go, I can look that it has rotational kinetic energy with this point being a reference. So in this situation, the object will have purely rotational kinetic energy. It has only rotational kinetic energy if it swings like that. But I can look actually at the problem also in a different way. That I can recognize that there is a translational motion because the object moves, and at the same time it rotates about that center of mass. So there will be another rotational kinetic energy about the center of mass. Kinetic energy depends on this where we choose the reference point. Do you understand me? All right. So by definition, we now recognize what is kinetic energy. Whenever we pick a certain point, whatever is the total kinetic energy of that rigid body with the point being a reference point is the rotational kinetic energy of the object. Kinetic energy, we can figure out that it must be related to this, how fast the object spins. So it is related to angular velocity of the object. And let's say that this is axis of rotation, and we consider rotational kinetic energy about this axis. If an object moves, well, by definition of rotational kinetic energy is the total kinetic energy in the reference frame of that axis. From definition of total of kinetic energy of individual particle, it is 1/2 of the mass of the particle multiplied by square of speed of this particle. I can recognize now that the speed is related to magnitude of angular velocity and how far the object is. I mean, the particle is from the axis. Yes, so speed of the ith particle is magnitude of angular velocity multiplied by the distance from the axis to the particle. The further the particle, the faster it moves. I can recognize that, well, because it's a rigid body, so all particles move with the same angular velocity. So I can take this magnitude of angular velocity outside of the summation. And now I can recognize what I have here. What do I have here? Moment of inertia of the object about the center of mass. Axis passing through the center of mass, or moment of about the axis, right? It's moment of inertia about the considered axis. So Well, in summary, therefore, the rotational kinetic energy is equal to about a particular axis of rotation is equal to 1/2 of moment of inertia about that axis multiplied by square of angular velocity. Let's take a look now at the total kinetic energy of an object. So, total kinetic energy of the object requires that well, it is a sum of kinetic energies of all particles. Now, each particle has kinetic energy equal to 1/2 of its mass multiplied by square of its speed. I now recognize that speed of a particle is it always can be written as this superposition of translational motion and rotational motion. So this is velocity of a selected point. We remember that one of the most convenient of those points is center of mass, but it doesn't have to be center of mass. I can choose whatever I want. Well, this term describes rotation about that selected point. Well, the next step is mathematical. I just multiply everything and group the terms. Now let's see what is what. What is what over here? What did I do here? Oh, right. Yeah, I pulled out constants in front of the summations. Right, because over here we have a square of velocity of that selected point. It doesn't have subscript I, so I have it outside. Over here, omega is independent of I. I could take it outside, and 1/2 is independent. Over here, omega is independent. 2 is independent, or 2 and 1/2 actually cancel, and VA is also independent. All right. And I group it in such a way that now we can recognize what is what. If I add the masses of all particles constituting the body, I'm going to get total mass of the object. All right, so here is the total mass of the object. How about if I start with that? So total kinetic energy of the object will have, the first term is total mass of the object times, and if I choose now conveniently this point, if this point is the center of mass, then it will be square of center of mass, which means that this expression now this expression over here represents what? 1/2 of mass of the object multiplied by square of the speed of its center of mass gives me not total kinetic energy. Which one? Translational kinetic energy. So this is translational kinetic energy. Let's now take a look at this expression. Look at this sum. What this sum represents. What is that sum? Moment of inertia, correct. Now I selected axis passing through the center of mass, so this will be moment of inertia about the center of mass. Do you see that? So I can write down that this is 1/2 moment of inertia about the axis passing through the center of mass multiplied by square of angular velocity. I can now recognize that it is also a certain kinetic energy, which well, I mean, you saw it just a moment on the previous slide. It is the rotational kinetic energy. What rotational kinetic energy? About the axis, or about the center of mass, correct. This is rotational kinetic energy about the axis passing through the center of mass, correct. So I wrote that this is rotational kinetic energy of the object about the axis passing through the center of mass. Now, over here, if point A is center of mass, think what will happen if I calculate this sum? Well, this sum will be, if I divided this sum by the total mass, it will be position of the center of mass, right? Now, if I consider that the reference point is at the center of mass, so that expression will give me position of center of mass with respect to center of mass. So it's a zero vector. So if I multiply this 0 vector by vector omega, I will get a 0, what 0? 0 vector. And then I multiply this 0 vector by velocity of the center of mass, I will get 0, what 0? 0 number, correct. Because over here we had vector product, now here have scalar product. So, total kinetic energy of an object is equal to translational kinetic energy plus rotational kinetic energy about the center of mass. Now, I want to point it out the difference, yeah, because now, if I look at this rod when it is swinging, does it identify what kinetic energies it has? It has rotational kinetic energy. Does it have translational kinetic energy? Does it have total kinetic energy? Yes, okay. Now, I want to talk about rotational kinetic. And so let's start with this. I can look at this, that this is purely rotational motion, right? It is, if I consider this point of the reference. So tell me what will be the total kinetic energy, how the total kinetic energy is related to the rotational kinetic energy about this point. Is it greater or smaller? I mean, which one is greater, which one is smaller? Who votes that total is greater than rotational kinetic energy about this point? Who, what did I ask? Who believes that total is greater than rotational? Who doesn't believe that total is greater than rotational? And those of you who don't believe, you are right. Total kinetic energy and rotational kinetic energy about that point are equal. This is purely rotational motion if I look at the problem this way. Now let's look at the other way, because those of you who thought that the total kinetic energy is greater than rotational kinetic energy, you were right if you defend rotational kinetic energy. If you consider different rotational kinetic energy, which rotational kinetic energy would you have to consider? About the center of mass, correct. Yes, so if object rotates like that about this point, it rotates like this about that point. Yes, so rotational kinetic energy associated, I mean, about this point is less than the total kinetic energy of this object. And what's the difference between them? The translational kinetic energy, correct. Look that object has, I mean that the center of mass moves, so there is a translational kinetic energy as well. Yeah, be careful not to confuse that. And I know that on test you will confuse it. Yeah, because I mean you will have to to solve a problem in which you will do that. I hope actually that when you try, because I gave you one of the problems is to predict motion of an object like falling like that. Yes, so now you can look at this two ways. One, I mean, at a particular instant, you can think that this is a purely rotational motion about the point, this point over here, where the string touches the yo-yo. Yeah, so you can look at that this is purely rotational motion. Or you can look at this that it is translational motion because center of mass moves, and at the same time this rotational motion. So think about it. It's not really assigned in the homework, but think about, I mean, for this problem. Analyze also energy. All right. Oh, I forgot actually to include work energy theorems, I think. Now, if a torque is exerted on an object, I'll talk about this Monday then. If a torque is exerted on an object, well, then we can also figure out what is the rate at which work is being done. Well, rate at which work is being done is referred to as power. And actually, those of you who are in mechanical engineering and you will analyze how motors work, this is an important fact. I mean, this slide is very important for you. So if you are a mechanical engineer, concentrate now. So let's say then we have an object which is rotating with angular velocity, and we apply a certain force or a certain torque, actually, even to make it well, to change the rate at which it rotates. Well, so I will consider now differential work. Well, differential work is equal to force times displacement. So actually this is work which affects the total kinetic energy of whatever the work is done, right? Because I'm multiplying force by the displacement of the particle on which the force is exerted. Now, the displacement of that particle is related to that angle. And I mark this angle because actually all particles will have the same value for that angle if it is a rigid body. So I can write down now that, I mean, I will introduce this vector d theta, which indicates, which is in the direction along the axis. It's a kind of artificial way of describing the angle, but it automatically says the orientation of the angle. And then this displacement vector will be vector d theta multiplied by the position of the point where the force is applied about that axis of rotation. So vector r is from here to there. Now, this is a mathematical identity. I'm not going actually to prove it now, but we can change the order in a particular way, by the way. So I have to take the first vector and put it at the very end. Now, the reason that I did that is because what is this product now? The torque. What torque? It's the torque about the axis, right? So here I have the torque about the axis. So now scalar product is commutative, so I can write down that this expression is equal to scalar product of the torque and that angular displacement. All right, so I marked torque and differential work. I mean, my conclusion is that the differential work is equal to scalar product of torque and this differential angle. Now, power is the rate at which work is being done. So if I divide both sides by time in which the disk makes this change in orientation, so if I divide it now by dt, on the left-hand side, I'm going to get power. On the right-hand side, I will have torque times angular velocity. So actually, if you think now about a combustion engine, it has certain characteristic of a torque. Depending on this, how fast the engine turns. Let's think now, for example, that we have a motor, or electrical motor has this property, that the torque actually is independent of this, how fast the motor turns. At what, I mean, when do we deliver more power? When the motor performs more, delivers energy at higher rate, or performs work at higher rate, when it turns slow or fast? Fast, correct. The faster it slows at the same torque, the more power it delivers. Yeah, with a combustion engine, it isn't the case, because it has a certain characteristic. So torque delivered by the combustion engine, well, the plot looks like that. It has a particular rate, or you can find actually in your manual what is RPM, revolutions per minute, that the torque has the maximum value. It's written in the manual. I mean, we never read those manuals though. But I mean, if you are a mechanical engineer, or even if you are a racer, you would be very interested in that. Now, additionally to this plot, you will have a plot of the power, and power will be this plot multiplied by by that rate at which engine rotates. So you will have another plot which says what is the what is the plot representing power dependence, and power will be always greater. Maximum power will be always at a greater rate of rotation than maximum torque. Actually, the distance between these two rates is referred to as elasticity of the engine. Yeah, so engine which actually is kind of elastic, so you can run it at very low rates, has these two far apart. All right, so this will be all for today then, and see you Monday.